What we've seen in this lecture so far is, given an algorithm or a function, we can very carefully, beautifully analyze its possible runtimes by counting how many times each operation occurs. Now, with dupe1 and dupe2, in order to figure out which one's better, we then said, okay, the characterization of dupe1 is like a parabola, and dupe2 is like a line. What we're going to do in this video is be a little more careful about what we mean by like a parabola by applying a series of 4 simplifications that will boil these tables down to their essence. So the first simplification we're going to make is going to be to consider only the worst case. We're going to ignore this best case situation, and our table ends up just being the worst case counts. The reason we do this is that often, but not always, the worst case is where we see the most interesting effects, or the most interesting differences between algorithms. So dupe1 and dupe2, for example, they have almost the exact same runtime on an array of all duplicates, but then when there are no duplicates, the difference is vast. Now there'll be counterexamples. For example, when we talk about quicksort later, there we'll care more about the typical case than the worst case, but often it's the worst case we care about. Okay, when it comes to our next 3 simplifications, I'm first going to let you do a little intuitive exercise that will motivate these simplifications. So in this little example here, I want you to imagine that we count up the number of operations for some function that's not shown. And in this case, the number of less than operations is 100n squared plus 3n. The number of greater thans is 2n cubed plus 1. And the number of and operations is 5,000. So what do you think would be the overall order of growth of the runtime of this algorithm here? Would it be linear, quadratic, cubic, or sextic? Or in other words, if we were to actually do an experiment and collect runtime versus n, would that curve look like a line, a parabola, or something that grows more quickly? All right, I'll spoil it now. Hopefully you've thought about it. The correct answer is cubic. And you might have had an answer which was purely intuitive, but I'll give you an argument for the correct answer, whether you got it or not. So let's suppose that less than takes around alpha nanoseconds, greater than takes around beta nanoseconds, and takes around gamma nanoseconds. So in that case, the total time would be alpha times the number of less thans, plus beta times the number of greater thans, plus gamma times the number of and operations. So if we look at this expression and we say, for a very large n, what is the shape of this overall summation of these different operations? Only the 2 beta n cubed term would matter. Now this is an incredibly important point that's hopefully intuitive to you, and if it's not, try plugging in some numbers and you'll see that only the 2 beta n cubed term matters. Now if you happen to know calculus, one way to think about it is take the limit of this entire function divided by n cubed as n goes to infinity, and you'll see that the only term that survives is this 2 beta term. But if you don't know calculus, it doesn't matter. Now, it does matter a lot that you understand why only the 2 beta n cubed term is, so if you didn't get it, pause right now and just really think about it and make sure that makes sense before continuing on. So given that observation, there are 3 simplifications we'll make to our table. This first simplification of the next 4, so overall it's the simplification number 2, is going to be to pick some representative operation for the overall runtime. So if we look at the 6 operations, it's fine if we just maybe consider only the number of increment operations because it has this parabolic term to it, right? Because our ultimate goal is to show that the whole thing is like a quadratic. So we sometimes call our choice here the cost model. The cost model in this case is the number of increment operations. And that's a term out of the optional Princeton textbook that I recommend as a possible companion for the course. I think it's a nice term. But basically we pick a representative operation and we throw away all the other rows of the table. Now there were bad choices, like it wouldn't make any sense to keep only the row that has n or a constant, but these 4 choices down here that have quadratic terms, any of those would be equally good choices. Okay. Our third simplification is going to be to get rid of our lower order terms. So if I have n squared plus n divided by 2, we'll throw away the n. And the argument there is simply that, well, the overall runtime, this n term doesn't matter for large n. Only the n squared term matters. And then our fourth and final simplification is going to be to ignore our multiplicative constants, to eliminate them entirely. We'll drop this divided by 2. Now you might argue with this one and say, well, Josh, wouldn't an algorithm that has n squared increments be much better than one that's like 1,000 n squared increments. And you maybe have a point, but you have to keep in mind that we've thrown away all these other rows that may have had important information that is even more significant. So what I would say is that unless you have a good reason to really truly believe the overall runtime tracks almost exactly like, say, the number of increments, this constant is not particularly useful, though you will see it in some analyses sometime. But in this course, it'll basically never. I don't think it will ever happen. So we'll be throwing away this constant here. All right. So to summarize that whole process, given our table, we have 4 simplifications. The first one is considering only the worst case, and the bottom 3 basically say we only care about the order of growth. So we're going to pick a row, throw away all the lower order terms in that row, and also drop the multiplicative constants. And so in the end, we take our big, beautiful gold standard characterization of our function, and we reduce it to this simplified table where we're counting the worst case order of growth of the number of increment operations as a function of n. Now, assuming that increment operations each take some constant amount of time, then the order of growth of the overall runtime of the function should also be n squared. And that's the whole process. So what I'd like you to do now is to try what we just did, but on your own, to take this table for dupe 2, figure out your chosen representative operation, reduce it down to the order of growth of the counts of that operation, and from that, try to infer the worst case order of growth of the runtime of the whole function. Okay? So in my case, I chose the number of array accesses. The worst case order of growth in this case is simply n. And thus, the overall order of growth of runtime is also n, since we assume that array accesses take constant time. But any of those bottom 4 choices would have been pretty good. All right. So to summarize our whole process that we come up with, which is a little painful, our process was to construct a table of the exact counts of all possible operations that could occur, and then to convert that table into a single worst case order of growth using our 4 simplifications. Now that's overkill, right? We do this just intricate, wonderful process of getting every single thing that Donald Knuth would be incredibly proud of, and then we throw away most of our work. It seems a little ridiculous, right? Well, if we use our simplifications from the outset, from the very start of our process, it turns out we'll be able to avoid building this table at all. We're gonna eyeball things, right? So instead of using like our speed gun to use lasers to measure the distance and speed, or the difference in speed between a race car and the space shuttle, we're going to be able to just use our eyes and kind of intuitively just say, okay, that one's faster. We're going to dodge this careful analysis and make things much better. And that'll be in the next video.